Hi, everybody. In this video, we're going to be talking about Unit 9.1.3, which is the rational and real number system. And so that's what you see here, this real number system, our title here. And we are going to talk about the different subsets that the system makes up. So the real number system is made up of natural numbers, whole numbers, integers, rational, and irrational. And the real numbers is like the entire umbrella of all of those categories, all of those subsets is what that's called. The other thing I want to talk about is this word real. I really hate the terminology here because it makes us think real versus fake. Well, you need to be thinking about real numbers versus complex numbers. And complex number system, the complex number system, we're not going to really get into at all in this class, but we do touch on it a little bit in intermediate algebra. But that's like, for an example, if we had an I in our answer, so it'd be like 3 plus or minus 4i, this would be what's called an imaginary number. Again, I hate the terminology there because it's not like a made up figment of our imagination. It's just part of the term they came up with for it to be part of the complex number system. And it's pretty cool system, but we unfortunately don't get to talk too much about it. But anyway, I wanted to bring it up because people will ask me, real, like, aren't all of our numbers real? Well, the numbers that we typically deal with in day-to-day life, they are part of the real number system and part of the system that you're used to kind of working within. The other thing I'm going to do is we are going to be filling out this diagram as we are talking about the different pieces up above. So I'm going to go ahead and fill in this part. And one notation I'm going to give you is this symbol. If you see that symbol, that indicates the real number system. So like if we were talking about the complex number system, it would actually be C, and then we put the bar over here. And that's just to indicate a capital boldface R, because otherwise it would take us forever, right? Like if we were trying to do a boldface R and we'd go like this, and then it looks really messy. And so we don't do that. We just go like, here's a capital boldface R in kind of our manuscript here. All right, so this entire box is the real number system. So this is all part of this real number system. And the one that makes up the smallest category, the smallest subsets, I want you to think about these as like nesting buckets. So the smallest bucket that we have is the natural numbers. So the natural numbers are also called your counting numbers. They're the numbers that you say, all right, kindergarten class, let's count to 5. Do we start with 0 or do we start with 1? We start with 1, right? If we're starting with kindergarten, 1, 2, 3, 4, 5. Do we have any fractions? Do we have any decimals? Heck no, we are not going to be talking about fractions and decimals on our first couple weeks of kindergarten. So this is going to be like 1, it's going to be 2, it can be 64 over 8, because what's that going to reduce to? 64 over 8 would reduce to 8. It could be the square root of 25, because again, what does that reduce to? It reduces to 5. So let's come up, and I'm going to fill this in. Natural numbers are our counting numbers. So again, we can fill in some examples. It's going to be 1, 2. It can be 15 over 3. It could be negative 14 over negative 2, because what is that going to be? It's going to be a positive 7. So I want you to think about this. Natural numbers are going to be our positive whole numbers. So I'm going to write that in there. There are positive whole numbers. That means no fractions or decimals or negatives. All right. Whole numbers. We've got the natural numbers plus 0. That's the only difference. It's kind of a ridiculous distinction. How I like to remember it is that there is an O right here in the word whole, and that always helped me remember. I remember having to learn these, and it helped me remember the difference between these two. I thought, okay, I can do this. This one has 0 plus all the natural numbers. So it's going to be 0, and then it can be any of the numbers I set up above. It could be -14 over -2. It could be 15 over 3. It could be 0 over 4 because that's going to give me 0. So it's going to be the whole numbers plus all of the natural numbers. So that's what this next category is. The next basket on the outside is whole numbers. And what is the only unique number? The only unique number to that subset is 0. And then it could include all of the rest of these. So it could be 1, it could be the square root of 25. It's going to be any of the rest of those natural numbers. All right, so let's come back up here. The next category, so we've got natural, whole. The next one is integers. Integers are going to be positive or negative whole numbers. So it's going to be the whole number set plus all of their negatives. So that still means no fractions, no decimals. So we would have like -4, -100 over 10, because that's going to give us -10. Now, some of you, I've had students say, now, wait a second, you just told me there's no fractions. Well, simplify it, right? Simplify this fraction. If it can be simplified into a positive or negative whole number, it's going to be an integer. So that's why. But fractions, like what I'm meaning is like 1 over 100 or -2/5. Those are not going to be in the integers or the whole numbers or the natural numbers. So let's come down here. Oh, and I'm also going to put this in here too, or it's going to be something like 0. So let's come down here. My unique examples, I'm going to try to remember my color coding scheme. My unique examples are going to be in black for this. So our next subset is integers. And if you want to remember this, it's positive or negative whole numbers. So that's going to include my unique examples. I almost wrote up one that's not unique. Unique examples could be -24 over 6, because that's going to be -4. It could be negative square root of 25, because that's going to be -5. Now my non-unique examples, let's pull in any of the others that I've already written up. It could be 0, it could be 1, it could be the square root of 25. Any of those. So that means the integers are made up of 100% of all of the whole numbers. They're made up of 100% of all the natural numbers, but they also include some negatives. But that still means up here, I'm going to reiterate this, re-emphasize this. For this, no fractions or decimals. So no fractions or decimals. All right, for rational numbers, that's our next category that comes out. It's a much larger category. Look at this root word of ratio. Ratio, what is a ratio? It's a fraction. So if a number can be represented as a fraction, it's going to be a rational number. If it cannot, look, here's that word ratio again, but then we've got irratio. That means not a ratio. If it cannot be expressed as a fraction, then it will go into that irrational numbers category. So let's fill in our definitions. A rational number is any ratio, there's that word, any ratio, use that root word to help you, of 2 integers. Now put your definitions together. That means we can take any 2 integers and we could put them, one in the numerator, one in the denominator, and that is going to give you a rational number. Or any number that can be expressed as a ratio or fraction. Also, it will include repeating and terminating decimals. So terminating decimals, think about what the Terminator did. He ended life, right? Terminating decimals, they don't end life, but they end. They're decimals that stop, they terminate. They no longer are going on forever, repeating. Okay, so that would be something like this. So a repeating decimal, think about this one. If we've got 4.3 repeating, 4.3 repeating, 3 repeating is 1/3. That is why 4 1/3. That is why this is considered a rational number, because is this expressed as a fraction, as a ratio of 2 integers? Absolutely. What about a terminating decimal, a decimal that stops, that ends? Well, think about 0.25. What is that as a fraction? It's 1/4. So you're asking yourself the question, can I rewrite that as a fraction? Well, it's 25 hundredths. It's 25 over 100. If you can write it as a fraction, it will be a rational number. Even a super long decimal, let's say we had negative 12.21643. Is that a decimal that stops, that terminates? Yes. So this is a rational number because it's tenths, hundredths, thousandths, 10,000ths, 100,000ths, right? So we would write negative 12 and it would be 21643. What did I just say it was? 100,000ths, tenths, hundredths, thousandths, 10,000ths, 100,000ths. So 100,000. That's crazy. But we can still write it as a fraction. So therefore it counts as a rational number. It also includes all integers, all whole numbers, all natural numbers. I'm going to go ahead and talk about irrational. Then I'll fill it in on the chart below. Irrational numbers are any number that cannot, I would highlight that, I would circle it, I would draw your attention to it. It cannot be expressed as a ratio. Numbers that are both non-repeating and non-terminating, they have to be both, and non-terminating decimals. Did I spell that? Terminating decimals fit into this category. So things like pi, that's an irrational number. So it's 3.14 and then it just keeps going on forever, and it's a decimal that doesn't terminate and it never repeats. Same thing with Euler's number, or same thing with the square root of 3. Put that one in your calculator. Square root of 3, you're going to get 1 point something. And then we put that in your calculator, it's 1 point something, and it doesn't ever repeat and it doesn't ever end. So it's going to fit into this irrational number category. Real numbers. Real numbers are rational and irrational numbers, which is why it's over our entire box here. And they combine to form the real numbers, which consist of any number along the number line. So if you put in your number line and it's 0 and it's 1 and it's -1 and it keeps going this way up to negative infinity, or I should say down to negative infinity up to positive infinity, it's going to be part of the real number system. And here we're going to define, in case you weren't sure about the non-terminating, non-repeating, we're going to define it for you here. So non-terminating decimals are decimals that continue forever. And non-repeating decimals are decimals that never form a repeating pattern. All right, so let's come down here. We've got to fill in some stuff here. We got to fill in our rational numbers, which are going to be over on this side. And our irrational numbers are going to be on this side. All right, so again, I'm going to put in my unique examples to the rational numbers like this. So I could write it like 1/3, which is the same as 0.3333, which is the same as 0.3 repeating. We've also got decimals that terminate, because it could be like 2 1/2 is the same as 2.5. It can also be negative. So sometimes I get stuck on my positive numbers here, but students have been like, what about negative numbers? Yeah, negative numbers go in here. Look at all the negatives down below in our other categories. So maybe we had negative 131.1. Well, that's the same as negative 131 1/10, right? Those are all going to be rational numbers. Plus, we have all of the ones down below. We could still say, well, 0. Is it also rational? Yep. What about the square root of 25? You betcha. What about, we could do 1 over the square root of 25. And so this is a unique example. That one should have been black. So 1 over the square root of 25, this would be 1/5, right? So that one's going to come in here. And we can pick out any of the other ones that we've already done, 64 over 8, and they're going to fit into that rational numbers category. All right, irrational. That is going to be things like pi, Euler's number. And again, this is the 2.72, and it keeps going on. It goes on forever. It never repeats. This is the 3.14. Same thing. It goes on forever. It never repeats. If we did like the square root of 3, the negative square root of 26, if we did square root of 13 over 2, any of those are going to be irrational numbers. We could also write something like negative 14.2167319 ... So that would include what you would look at. You would say, do I see any repeating pattern here? No. So then that means that I can form the assumption that these numbers never repeat. And because I've got the ... that means it doesn't ever terminate. On the flip side, let me give you another example over here, because I know this can be confusing. If instead, I'm going to take that same number and I did negative 14.2167319 and it ended, that goes into the rational numbers category, because though it's a long decimal, it's a decimal that terminates. Same thing. I'm going to put it right here. If I did negative 14.216216216 ... Look at that. We see that there's a repeating pattern and it goes on forever. So we could actually rewrite this as negative 14.216, and we'd have the repeating bar. That is a repeating decimal. It goes on the rational number side because we would be able to express that as a fraction or a ratio. I know this can be confusing, so I would highly recommend as you work on this topic in your EdReady, you keep this page handy, because it will really help you out as you work through that. All right, so what I would like for you guys to do, I would like for you guys to work through this table. I am going to go through it, but I also want you guys to take the opportunity to work through it, because typically in class, I would have you guys work through this one together in class with your neighbor, and then we would share out together as a class and just kind of make sure everybody's answers are right. So pause the video. I know that's hard to do sometimes, but pause it. Otherwise, this stuff doesn't get into your brain because you're just watching me do it rather than you trying to do it. So pause the video and see how you do on these, and then unpause it and watch and see how you do. Or watch me do a couple and then pause it. All right, here we go. It says complete the chart below to test your understanding of the number system. So it's asking, is negative 0.84 repeating? Is that a natural number? No, there's no decimals, no fractions. Same thing with whole. No decimals, no fractions. No decimals, no fractions. There are no decimals in any of these first three categories. No decimals or fractions. Maybe that would help. So the first time we get decimals or fractions is here. And then you have to decide what type of decimal is it. If it's a decimal that repeats, it's absolutely rational. So it's going to be negative 0.8. Oh, sorry, we don't need to write it there. I just need to do a check mark. My bad. Getting excited about the repeating decimal. So we're going to check it here. If it's rational, it absolutely cannot be irrational, but it will always be real for that. All right, for square root of 9, first reduce it. Square root of 9, that reduces to 3. What's the smallest subset that fits into? Come back here. The smallest subset. If it's natural, take your finger, put it inside the inside bucket, pull it all the way out. It's going to be natural. It's going to be whole. It's going to be integer. It's going to be rational. Will it be irrational? Heck no. This is like our dividing line. This is a dam that cannot be crossed. So if it's part of this half, it cannot also be part of this half. Those are mutually exclusive. So we've got natural, whole, integer, rational, and real. What about 0.25? Well, again, we don't have any decimals in these three. Here you're asking yourself, can this be expressed as a ratio or a fraction, or is it a decimal that terminates? Is it a decimal that stops? Yes. So it's rational and it's real. Square root of 5. That is going to be irrational and real. Because again, if you put that in your calculator, we're going to get a decimal that goes on forever and it doesn't repeat. 1/2. You can either think of it like this, it's a decimal that terminates, or it's a fraction. It's a ratio of two integers. It's going to be rational and real. 1.213 repeating. 213 repeating, it's a repeating decimal, which is the one that has repeating decimals. Hopefully you got it. Rational and also real. All right, 1.2132135. That 5 breaks the pattern, but we have a dot, dot, dot. So we have a decimal that goes on forever and it does not repeat. Which one is that? That's irrational and real. We have a decimal that terminates, a decimal that stops. Or you could rewrite that as 1 and 213 thousandths. Which one is that? That's rational and real. -5. All right, we can come back over here. -5. Which one is it? Which one first starts including negatives? And it's integers. Integers is the first one. It starts including positive and negative whole numbers. So it's going to be an integer. Will it always be a rational number if it's an integer? Yes, rational and real. 15/7. Well, that's a fraction. So that's going to be rational and real. You should check that one out in your calculator. Do 15 divided by 7. It's kind of interesting. It actually has a 6-period repeating pattern, which means it's 6 digits that repeat. So you should check in your calculator. It's kind of a cool number to look at, because you might, if you changed all these into decimal form, you might look at that and think, oh, that's irrational. But back up, hold the phone, look at this. If it can be expressed as a fraction, period, it will be a rational number. All right, let's reduce this. This is the same as 2/5. So 2/5, because it's the square root of 4, which is 2. The square root of 25 is 5. That's rational and real. Pi, I gave that one to you earlier. Irrational, real. 0, you got this. Whole, integer, rational, real. Now here, you are looking at these. Again, you should have paused this. I'm hoping you've worked through these. If you haven't, you should go pause it right now. And work through these on your own. So we are going to correct the false statements by changing the underlined word if necessary. If it's not false, we're just going to write true. If it is false, we're going to change this to all, some, or no. So those are our choices: all, some, or no. And one thing to keep in mind, let's draw up our little diagram to help us. So we've got irrational over here. And then we've got rational over here. And then it's natural, whole, integer, rational, and then real is over the entire thing. Okay, and these are like our small buckets, right? So here we go. Some whole numbers are also irrational numbers. So you're asking yourself, does this subset cross over this subset at all? No. That one is false. So that one should be no. No whole numbers are also irrational numbers. Next one. Are all of the natural numbers also integers? Well, you're asking, throwing around my calculator. You're asking yourself, are all of those natural numbers, that smaller subset, that smaller basket, is it inside that, is the entire basket inside the integers basket? Yes. So that means 100% of these are part of this bigger set here. So this one's true. Some rational numbers are also integers. Some of these rational numbers are also integers. So you're asking, okay, what about some of the rational numbers, like 15/3? That's a rational number. Is that also an integer? Yes. So that one is true. No irrational numbers. So none of these are part of the real numbers. False. That should be all of them. This one says all integers are negative. True? False. All integers are negative. That one is false. Some integers are negative. Sorry, that should be here. Some integers are negative. No rational numbers are also irrational. So do these intersect at all? So none of these are also these. True. All non-terminating decimals are irrational numbers. So this one is saying all non-terminating, so decimals that never end, are irrational. I like that question. What do you guys think? All non-terminating decimals, so decimals that never end. 0.33333. That's a decimal that doesn't end. What is that? That's 1/3. Is that an irrational number? No. So some, so this would be some. Some non-terminating decimals are irrational numbers, like the square root of 3. Or if I had negative 1.1314667, and that keeps going on forever, that's a non-terminating decimal, but it also doesn't repeat. So that one should be false in some. All right. I know that's a lot of info. If you guys have questions, be sure you ask me in class, or be sure you post in my post in the help forum, or send me a text, send me an email, ask me in class. I'm happy to answer your questions. That's it for this video. Thanks for tuning in.